Hi, I'm Alistair, I'm a games designer, and in this video I'll show you how to make this magical glyph puzzle where players use their fingers or the tip of a wand to trace out glowing patterns between a set of nodes. Now when you activate a pair of connected nodes, a trail of light appears and illuminates the path between them. You can continue touching more nodes to add new segments onto the path. And when the shape drawn matches one of the predefined glyphs, the controller recognises it and triggers a relay output which can release a maglock. Perfect for escape room games. Now at the heart of this project is a single continuous strip of programmable LEDs, WS2812B or similar, laid out in a shape like a rune, a constellation or your own custom design. Now the physical order in which the LEDs are laid out is not important, just that they're all connected in series. So you can just position them in whatever way makes the wiring and layout easiest for you. The code remaps the LEDs from their index position along the strip and assigns them into logical groups, these circular rings of 8 LEDs around each node, and these straight line paths of different lengths that connect them. Now, simply turning LEDs on and off can make a project look very digital and electronic. So to make this seem more like a magical glow, I've defined some LED animations with fading and colour changing effects that represents the state of the components. So when you activate a node, it becomes highlighted with a rotating yellow swoosh. And as you extend the path, the most recent node touched becomes the new active node and always represents the head of the path from which new segments will get added. Now the LED segments drawn between connected nodes are not lit up with a solid colour, but rather they cycle slowly through a kind of a green-blue palette. If players wait too long, then the puzzle times out, the path fades and the controller simply resets. Alternatively, if players attempt to draw a path between two nodes that are not connected, that's an error. So the path will glow red and then fade out and the puzzle resets again. But if players successfully trace the path of one of the glyphs that's defined in the code, then the path turns golden. The controller activates a relay. You can have as many different glyphs defined and each one can activate a different outcome if you like. Now these animations are all defined in the code, which I'll explain a little bit later in the video, but obviously you can change them however you want. Now let me talk a little bit about the sound effects. Now in a lot of my previous projects I've made use of audio modules like the DF Player Mini or one of these DY players. You send them a command over a serial interface and then they play back the corresponding MP3 file from an SD card. They're cheap, easy to use, and I would still recommend using these for adding audio to most projects. But I'm not actually using them here, and the reason is because of latency. Basically, there's a lag between the moment that a trigger is sent from the controller to one of these modules, then that command has to be received and interpreted, the file loaded from the SD card, sent through the MP3 decoder, and then sent out to the line output. And that whole process takes about 200 or 300 milliseconds until the audio plays. Now, a quarter of a second might not sound like very long, and it's fine for most situations if you want to play a sound effect to accompany a button press or a mechanical lever. But when you want a sound effect to accompany a touch input, you really need something more responsive than that. Otherwise you get this disconnect between the haptic sensation of your fingers touching something, but the sound effect only coming a quarter of a second later. So I'm not actually using any external audio modules here at all. I'm generating the audio output directly on the ESP32 itself, sending that to an amplifier via the built-in I2S interface. Now that does have a few limitations. I'm constrained by how long the audio samples can be because they've got to fit in the same 4 megabytes of memory as is holding the program code. I also need to make sure that I don't overload the CPU with too much work, otherwise it might make the LED animations stutter. But the ESP32 is a dual core processor. If you're familiar with programming for Arduino, you'll probably know that you have a main program loop and instructions run sequentially one at a time. If any task takes a long time, it blocks the next instruction in the queue until it completes. Now the ESP32 chip I'm using is a dual core processor, and that means that you can perform 2 tasks in parallel. So I can run the LED animation loop on one core of the processor and then perform the audio processing on the other core so they don't interfere with each other. But before I show you the code that does that, let me just say a little bit more about the inputs. So each of these nodes is wired to one of the touch-enabled GPIO pins on the ESP32. So again, there's no additional external hardware used here. You can use the touch-enabled input pins to detect a finger touch, but also any metallic object, a liquid, anything that causes a change in capacitance at the GPIO pin. Here I've just got some screws, which I've connected a wire that's going back to the GPIO touch pin on the other side. So here's the components on the back of the board. I've got my ESP32, which is connected to an I2S amplifier, and that's taking the sound output to this speaker here. Then the blue wires, these are all connected to the touch input pins, and then they're wrapped around these screws which go to the front of the board, and that's how we detect when the nodes are touched. I've got a relay module here, that's what's connecting the 12 volt power to the maglock on the front that is released when a glyph is made. And then I've got all of the LED strips, these are connected via the 5 volt ground and data lines here, and then that extends through to the strips on the front of the board as well, which is connected through like this. So now you've seen the hardware in action, let me show you the code that's running on the ESP32 that makes all of this work. So it's all contained in a single sketch, but it is quite long. It's 540 lines. So rather than go through it all in detail, I really just want to focus on those elements that are more interesting, more unique to this puzzle, or those that use slightly less common functionality that you might not have seen before. So let's start with the audio, and that's handled by these three include header files that I've got at the top of the sketch here, which are part of the Arduino audio tools library that you can access at this GitHub link. And the way this library works is that it defines an audio processing pipeline. So you start by specifying a source, which could be a microphone input, an MP3 file on an SD card, a stream from an internet radio station, or whatever. And then you pass that audio stream through one or more processing steps, which could alter it in some way, change the EQ, apply an echo, or set the volume. And then you send it to an audio sync or output, which could be a file or broadcast it over Bluetooth or send it out to a speaker. Now the audio source I'm using is LittleFS, which is a small file system operating on the ESP32. So rather than defining my audio samples as bytecode directly in the sketch, I can place MP3 files into the data subfolder of my project, and then I can use the LittleFS uploader in the Arduino IDE to upload those files onto the ESP32 and manage them as separate files, a little bit like uploading to an SD card. I can still reference them from my sketch, but they're uploaded into a separate area of memory used for file storage, which means if I edit the code and upload a new version, I don't also have to copy the audio files across every time. Or I could swap out the audio files without needing to re-upload the sketch. They're treated as separate resources. So to do that, I'm including this LittleFS audio source header here. Now, because the audio files I'm copying across to LittleFS are encoded in MP3 format, I also need to add an MP3 decoder, so I'm using the Helix decoder here. So my audio pipeline is actually very straightforward. I create an audio player object that loads from the LittleFS file source, it processes it via the MP3 decoder, and then it sends it to the I2S output, which I've wired to an amplifier. Now if you wanted to use a different audio source or add more effects, you'd add in the relevant additional headers to use those. And there's lots of more advanced examples provided in the Arduino Audio Tools library, so do take a look if you're interested in audio processing. And then to use the player object, it's rather similar to any other audio player you might have seen me use in previous projects. You simply specify the index of the file that you want to play. And so I've uploaded 5 sound effects from the data subfolder, so they're just indexed 0, 1, 2, 3 and 4. And then in my loop function, I call the player.copy method here, and that's responsible for streaming the data of the selected file to the audio output every frame. So now let's take a look at the LEDs. As with many of my projects, I'm using the Fast LED library. This is a fantastic library for controlling any kind of programmable LEDs. Now I'm using 5 volt WS2812 LEDs, so in my setup function here I call the add LEDs method, specifying the type of controller I'm using, and those are all connected in a single strip to GPIO pin 5. So I've got a single array called LEDs which contains the RGB values that I want every LED to light up. And then when I want to create any animation like the fading or colour change effects that I showed you, all that does is requires calculating different values for the appropriate elements in the LED array and then pushing them out to the strip, which I do in these lines here. Now to determine which LEDs are affected by each animation, that's defined at the top of the code in a whole bunch of arrays here, for the rings of LEDs around each node and also for the segments that connect them. So starting with the nodes, I've got a structure here that defines the index of the first and the last LED in each circular ring. And then for the segments that connect them, I've also got the first and the last LED and also the index of the nodes that that segment connects. So the very first set of LEDs in the strip, for example, the first 8 LEDs, which are indexed between 0 and 7, connect nodes 1 and 0. The next 8 LEDs, well, they're indexed from LED 8 to LED 15, and those connect nodes 0 and 2, and so on. So I've got a total of 95 LEDs that are used in these segment strips. The very last segment here ends with LED index 94, and then I have the LED rings in the sections of the strip immediately following that. So the ring of LEDs that is around node 7 is actually connected next, and that has the LEDs from 95 to 102. Then we get the ring around node 8, node 6, etc, etc. So this might seem like they're sort of in a jumbled up order, but the advantage is that it means it makes the wiring much more straightforward. You can reduce the total length of wire you have to use and arrange the segments in whatever shape is convenient. Then you just update these arrays at the top of the code to reflect however you physically laid them out. And of course you can adjust the number of LEDs, the number of nodes and segments here as well. Now while we're here, let's also take a look at this array here, which defines the glyphs that are recognised. So I've just put 2 examples here, one in the shape of a question mark and one in the shape of a bow tie. And these are the numbered segments that need to be lit up for this shape to be recognised. The last number here, this is the total number of segments that form that glyph. And we also compare this to make sure that not only have all these segments been lit up, but also no more. Because we don't want the case where the player could just illuminate every segment and for that to count as the glyph being complete. It needs to have exactly 4 segments lit and for those to be these segments. That's how we define the glyph here. Now let's take a look at the inputs. So here I've got the array of input pins which I'm using for the touch inputs. Now ESP32 has a total of 10 GPIO pins that support touch input. I'm using 8 of them. And these are mapped to GPIO pins 27, 15, 4, etc. I'm also defining a threshold value that's used to alter the sensitivity of those inputs. So when you use one of these touch pins, it's a lot like using an analog input. You'll get a number value returned that represents the capacitance detected at the pin. Now when you touch human skin or another surface against the pin, the reading will decrease. And when it lowers below this threshold value here, that's when we'll determine that the touch has been made. So if you want to make the touch sensors more sensitive, let's say you've put a layer of perspex or wood in front of the sensors, then you want to increase this value. If you want to make it less sensitive, you can lower it down. Alternatively, you don't have to use touch sensors at all. You could use normal arcade buttons or other inputs. You just have to replace the input system, but you could keep the rest of the logic used in the code exactly the same. Now, I've defined various states up here which represent the different states that the puzzle can be in. And I'm going to use these in a simple state machine that determines the actions that the player can take and the behaviour that the controller has based on the current state it's in. Now, I've used state machines in almost all of my escape room puzzles, and I do recommend it for any kind of moderately complex system. It's a lot like imagining your code as a flowchart that says, where are we right now? What are the different possible actions that can occur that will trigger a transition us to a new state? And then when we get to that new state, what are the set of actions that occur there? So I've defined a number of states that the puzzle can be in. It can be idle, which is where we're just waiting for a player input. It can be animating a segment after a pair of connected nodes have been touched and it's extending the line between them. We kind of just completed a segment, the player might have made an error or timed out. And depending on what state the puzzle is in, that affects what inputs the player can make, what sound effects are played, and what LEDs are being animated. And another reason why it's useful to define this in a separate variable is to do with synchronizing the systems that control all those different behaviors. Remember I said that I'm executing the LED animations on the audio code and the rest of the game logic across different cores of the processor, but I need to make sure that they're synchronized with each other effectively. So I'm going to use this state variable across the functions that are running on the different cores of the CPU. So let me show you how I do that. If we scroll down the code here, we find the main program loop. So this is responsible for reading the touch inputs. It's also got a serial connection which I use to read any values pressed on the keyboard. I included this originally just for testing purposes, and it means I can just press the number keys to simulate a touch on the corresponding numbered nodes. Now we also check for certain game conditions based on the current state. So if we're currently idle but a node has been pressed in the past, but it was pressed more than 5 seconds ago, that's our condition for timing out and resetting the puzzle. Otherwise, if a segment has just been completed, we need to check whether her glyph has been made. So we're executing various blocks of conditional code logic based on the current state of the puzzle. And we've also got this line here, which, as I mentioned, services the I2S audio stream. But notice that it doesn't contain any code at all to do with LEDs. That's handled in this separate function here, which I've called LED loop. So again, at various points, this references the value of the state variable. We've got an idle state, and when we're in the idle state, what we have is we have that whoosh effect that goes around the circular rings around the nodes and kind of lights the current node up a yellowish hue and then advances in a rotation around the ring. We also assign a kind of a bluey green shimmer to the segments that have already been drawn. That's done by calling this getHue function here. And the getHue function itself, that's actually defined near the bottom of the code. And what that does is it uses one of the fast LED built-in noise functions. So this applies a random noise offset based on the time that has elapsed, and it looks up into an index and assigns a hue within the values 80 to 160, which is kind of the greeny blue area of the color spectrum. So that's what gives it that nice kind of undulating hue, watery effect and things like that. It makes it seem more interesting and more animated rather than a solid block color here. Now, if we're adding a new line segment, that's managed in this section here. Now, I mentioned I don't really like the digital effect of just lighting up one LED at a time. I want to make a softer, more gentle fade in. So what I'm actually doing here is I'm working with fractions of LEDs and gradually lighting up the LED in stages. So I increase the fractional brightness of the LED at the tip of the line. And in order to make sure I'm animating that in the right direction, I've also got a variable here. So let's say we've got a segment that connects nodes A and B, but the player could touch those two nodes in either order. So I need to keep track of whether I'm animating it from A to B or from B to A. In both cases, the segment will end up lit, but I just want the animation to play in the right order. So that's what anim direction's doing. And then we've also got the animations for when a glyph is made, makes it gold and then fade out, or if an error is made and we have the red fade out. So there's quite a lot of logic here that's continuously updating and animating the LED values based on the state of the puzzle. And we want to keep this running at a steady frame rate and not be interrupted by or cause interruptions in the audio or the input processing. So that's why we run it on a separate core. And we do that in the setup function on this line here. So this function specifies that you want to execute a task tied to a particular core. Now, I2S audio normally runs on ESP32 core 1, so we're going to specify that we want to run the LED loop function on core 0 instead. And that's all you need to do. These other parameters here are largely defaults that you don't have to worry too much about. And this task will be created once and called on setup when the ESP32 first starts up, but then it will run over and over forever. And the reason it does that, if we just go back to look at the LED loop function again, notice that all of the code here is wrapped in a while true loop. So this is an infinite loop that's just going to run over and over again on core 0, while the other tasks run as normal on core 1. Now there's only one more important thing I need to mention about the way that this secondary LED loop works, and that's right at the end. You'll see a call to a function called vTaskDelay. Now, you're probably familiar with the regular Arduino delay function, which is a way you can introduce an artificial pause in your code by just blocking for a set amount of time. And that's similar to what we're doing here. We're slowing down the animation loop slightly, but the ESP32 has something called a watchdog, which is a little bit of code that runs in the background to basically check that the program hasn't hung or accidentally entered an infinite loop. So the watchdog has a timer which resets on each iteration of loop, and if that timer runs for too long, the watchdog panics and it sets off this alarm resetting the ESP32. So if you were to have an infinite running task just in a while loop that runs over and over again normally, that would set off the watchdog alert because it hadn't handed control back to the watchdog in a long time. But we want LED loop to run infinitely to continuously service the LED animations. So what we do inside the end of each loop, we call this vTaskDelay, and that implements a small delay before continuing, but it also yields control back to the watchdog briefly, just to let it know that everything's still running okay and everything's fine and not to panic. So if you do start experimenting with running tasks on particular cores, and if you want those tasks to run infinitely, as I do here, like a secondary loop, just be very sure that somewhere in your loop you either call yield or you call this function here, which implicitly calls yield, so that the watchdog is okay. Now the rest of the code is all pretty standard stuff. We've got the logic when you add a new segment, which includes checking whether we've already drawn that segment or not, and also playing the sound effect, adding it to the array of segments that we've already drawn so that we can know when a glyph has been made. And we've also got things like checking the glyph, and then if one has been made, activating the relay pin here. Then we've got some basic helper functions that deal with getting the inputs, logging some debugging information to the serial monitor and things like that. That's about all the code there is. So I hope this video might have introduced you to some technical topics that maybe you haven't seen before, using I2S to generate audio directly on an ESP32, using LittleFS file storage, creating dynamic LED animations, or using parallel processing across multiple cores. And hopefully I've also demonstrated some practical uses for those features in an escape room puzzle. Now, I was only able to give a fairly high-level overview of some of those features in this video, but I'll be making the code available to download on my Patreon account, and I've tried to provide comments throughout that explain every section in more detail. I'll also upload the wiring diagram there, so if you're interested in building this project or in any of the other escape room projects I've featured on this channel, please do check that out. I'll put a link in the description below. I also have a Discord server where you can get support and chat to other folk around the world who are making some really cool playful technology projects. Of course, you can also subscribe to my channel here on YouTube to see more of my tutorial videos. And I just wanted to end by saying thank you very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.